So hello everyone, welcome to the second lecture of the course. So the disclaimers remain the same. Now needless to say, we are living in an era of smart revolution where these smart devices, smart watches, smart mobile phones, tablets, and even these Google Home and all these entities have become a part of our everyday lives. And they have made our lives much more comfortable than ever before. But have you wondered what has driven this smart revolution? So it has actually been driven by the advancements in the transistor technology. So from one perspective, I would describe transistors in the form of, like, I'll give an analogy of transistor to the human body. So like the cells constitute, or the cells are the basic constituents of our human body, these transistors are kind of the basic constituents of these smart devices. And it's really interesting to note that these billions of transistors enable your smartphone or smart devices, and how this small chunk of silicon is actually dictating our lifestyle. So this is simple analogy that these cells are kind of cells are related to human body in the same way the transistors are related to these smart devices. Now this table simply shows you the number of transistors in the modern day processors. So Apple M1, which is the latest processor from Apple, you must have heard about that. This also contains some of the artificial intelligence accelerators. Also, Apple A4 Bionic chip was the most recent, innovation from Apple. So if you count the number of transistors over here, you will see that the number of transistors has already gone into the billions. Like there are already some billions of transistors. So there are like 16 billion transistors in Apple M1, 11.8 billion transistors in Apple A14 Bionic. And if you look at the technology which has been used to make these devices, it's already 5 nanometer technology. Now, when we read about Intel 4004, which was the first microprocessor, which was a MOSFET-based kind of microprocessor, we found that all these transistors were handcrafted, and even they were placed or laid manually, right? So that kind of a design, when all the transistors are kind of handcrafted and they are laid manually, that is called full custom design, because there the engineers have the liberty to kind of design each and every transistor on their own, and also to place them in the circuit according to their own wishes, right? However, as the number of transistors goes into this billions of range, like if the number of transistors is in some billions, how is it even possible to lay down all these transistors like on a chip, or even design individual transistors? So as the number of transistors increased from 2300 in Intel 4004 to some millions to some trillions, not trillions, but some billions. So still we have not reached that trillion mark, right? That should be noted. So as the number of transistors increased to some billions, handcrafting individual transistors became almost impossible because there are so many of them, right? So what we did? So what designers came up with is a divide and conquer approach, same as the British. So what they did was, they divided a digital system into several levels of hierarchy. So the different levels of hierarchy, or the lowest level of hierarchy, is the device. And then several devices combine to form circuits, which forms the next level of hierarchy. Several circuits combine to form logic gate, which is the next level of hierarchy. Then several logic gates combine to form modules. And these modules, or if you combine several modules, then you end up having a digital system. So it can be, related to our human body as well. So these devices or these transistors, they act like cell. As cell combine to form tissue, this tissue can be related to circuits. As tissues combine to form organs, these organs can be related to logic gates. Then the organs combine to form biological systems like digestive systems and all. So that can be, related to a module. And all these biological systems together combine to form a human body. So that can be related to the digital system. So any digital system, any modern digital system, if you look at it closely, it is definitely organized in this hierarchical manner, and it becomes really easy to design them that way. Let us look at how. So each of the entities, so as you move above this hierarchy, when you go from device to circuits, the circuit designers would treat this device or this transistor as a black box. So all of the entities in the previous hierarchy are kind of treated as a black box. That is, we are only interested in their behavior. We are not interested in their detailed kind of characteristics. So for a logic gate designer, a circuit is kind of a black box. For a module designer or an architect, this logic gate is kind of a, I would say, this logic gate is kind of a black box. So it goes like that. Now, from full custom design, which is handcrafting individual transistors, we have come to a level where we are not exactly fully handcrafting the chip. What we are doing is we are doing something which is called semi-custom design. So at each level of abstraction, these entities can be reused. For instance, if you are making logic gates, we have some library of these circuits which can be used and reused for making logic gates. When we are making some module, there are some library of this logic gates which can be reused. So what we want for this semi-custom design, we definitely need a library of all these entities at different levels of abstraction or at different levels of hierarchy. Now, we can also relate it to coding. So, when you code, there are some, standard library of routines or functions which can be called anywhere in the program. So you do not need to, write those routines or those functions again and again. You do not have to repeat it. That is the same is the case with, nowadays semi-custom design. So let us look at how exactly the present present digital design industry is, progressing, or what exactly happens in the semi-custom design, which is the common norm or common practice in present, microprocessor industry or present digital design industry. So the semi-custom design flow looks something like that. So at the top level, you have a behavioral model, or what you do exactly is you kind of use a high-level description language. The two most common form of HDL is Verilog and VHDL. So we would be also studying studying about Verilog or VHDL, how to write codes in them in this course. So what you exactly do is you write a code for the behavioral description of your digital system. For instance, let's say if you want to write a HDL code about a gate, you will just relate your input to the output. You'll just kind of write the behavior code for the input-output relation, or the truth table of that case. You're not interested in how exactly it will be implemented on hardware, or what exactly are the circuits that you will implement. What exactly are the circuits that would be implementing that. At behavioral level, you treat it as a black box. You only relate the inputs to the outputs. So what you feed into this, what you write a code in HDL is a behavioral model of the system. Now that HDL code is kind of given to a logic synthesis tool. Now what this logic synthesis tool does is it converts it into a gate netlist. That is, it tells you what are the different gates that are that will implement this logic, that this relationship between input and output, which you have defined in the behavioral level, and how exactly those gates are interconnected. Now these gates and all, they are most common approach to make these gates as standard cells. So I'll let you know what exactly is standard cell in the later lectures, but standard cells basically are laid out having same height when they are laid out, or when you make their layouts. So that I'll discuss later. But once you get the gate netlist, what you do is you now formulate test cases, and then you check the functionality of the system. I mean, whether it's working fine with all the sets of inputs and outputs that you want. That is, you formulate some test cases. I mean, you do some nominal test cases, then you just look at the system's behavior, and then you come up with some nominal test cases, you come up with some extreme test cases, or where the system will give you a 0 output or a 1 output, and then something in between. So something like that, you come up with these test cases, the test benches, and formulating this test bench to check the functionality of system, that the system is working for all the sets of inputs and outputs. This kind of approach is called RTL verification. And this is the most popular job that is available in India right now. So if you go to Intel, Qualcomm, or any such digital design company after a bachelor's, most probably you'll be doing this RTL verification. So after RTL verification, what happens is, now about the gates, about their interconnections. Now, once the functionality is satisfied, you go ahead with the floor plan. That is, you have to plan where exactly these logic gates or standard cells are going to be placed in an IC. So the constraint here is that, your IC area or your chip area or your die area is already known to you. Now, once the area over which you have to integrate these transistors is known, then you need to plan where exactly you will place these logic gates or standard cells. So once that floor planning is done, then what you do is you place these standard cells or these kind of gates which you obtain via this gate netlist. So once you place this standard cell, now the second part of it comes, which is called routing. So what you do is you also have to connect these standard cells via some interconnect wires. And there can be several possible configuration of these interconnects. And this is called routing. So out of this, which one will you kind of, choose? Which kind of routing will you choose? Which kind of placement and which kind of routing will you choose? Which combination of placement and routing will you choose? So, now comes the part which is known as specification. So whenever as a designer, so what happens exactly in the industry is, the consumers, for instance, for microprocessor industry, it can be a mobile, it can be made for mobile, it can be made for your laptops, it can be made for your workstations, for servers. So different consumers. So for a mobile, like for a microprocessor industry, these are the consumers, the mobile companies, the CPU companies, the server companies. These are your consumers for a microprocessor company. Now these companies will give this microprocessor company a specification. For instance, if they are, if they want a microprocessor for mobile phones, they'll say that, okay, I need a microprocessor which runs at a certain speed, but it should consume a very low amount of power because we want to drain our battery as low as possible when we are working with mobile phones. But at the same time, the same industry gets a spec from, if the same industry gets a spec from a server company, for servers, speed is more important, right? So they would say, do not care about energy. I mean, pay only little attention to that, but try to make your processor as fast as possible. So that is what the spec will be given by, a server company. So different consumers come to these microprocessor companies with different demands. And then depending upon those specifications, these companies try to, design circuits. So now, once you have, gone through all these processes, once you have written the behavioral code, once you have synthesized it using logic synthesis tool, once you have, placed these logic gates somewhere on the chip, and once you have interconnected them, or once you have, routed them via some form of routing, then you check if the system meets these specifications or not. If yes, then we can go ahead with, chip fabrication. If no, we have to change the placement and we have to change the routing. And this is called optimization of PNR. So placement and routing in the industry, it's usually known as PNR. So once PNR is satisfied, after multiple iterations, what we do is we send it for fabrication. And fabrication is done by dedicated foundries. So you have global foundries, you have TSMC, which is the largest foundry. So what exactly happens is in these foundries, they accept the designs only in a particular format. So they have a particular format and they'll accept these designs only once you send them the design in that format. Otherwise, they won't fabricate. And that design format is called, GDS2 file. So you start with HDL or RTL level, and then when you go through all these processes, you convert your RTL to GDS2, and then you send it to the foundry for tape out. So this is the particular flow which is nowadays taken in the industry. However, let me tell you that your life has been made more easy by automating all of these. So nowadays, this placement and routing is also automated. So what exactly happens is these iterations and all, as a designer, you don't need to care about them. What you need to feed to these tools such as Cadence Encounter is, your behavioral like HDLs. So HDL of your individual components. For instance, if you're, making a CPU, then you have to feed the HDL of different components like ALU and all. And at the same time, you have to feed in the specifications in the form of, the maximum delay that you can tolerate and so on. So once you do that, the tool itself kind of, it synthesizes your like netlist. Then the tool itself kind of places the standard cells. It is done by its own. I mean, it does it by its own. However, there can be some cases where it may not be able to achieve or fit those specs. So in that cases, custom kind of design becomes important or manual intervention becomes important. But most of the designs, these tools are so advanced. They use some optimization tools and they are so advanced that, they place the cells and they optimize the placement such that you are able to reach those specs. And they also do that for routing and all. And in between placement, like after this placement, there is also one more thing which is being done is, they place kind of power rails and ground rails that I'll discuss later in this lecture itself. But you should know here that, nowadays, these entire process, like these iterations are kind of automated. So what you need to provide to these tools like Cadence Encounter is simply the behavioral models, that is the HDL files for individual components and the timing constraints or, the specifications. Once that is done, the tool will automatically, generate these things, and it will kind of, automatically give you the final GDS2. So that is the beauty of, these optimization things nowadays. But again, nothing comes for free in VLSI. So VLSI is similar to like nothing comes for free. So you will see that later why exactly this automated design, it has also some shortcomings. So now let us compare the different digital system design approaches. So full custom design, which was done previously, where you used to handcraft all the transistors, their location, everything. So what is the difference between full custom design and semi-custom design? I've just tried to summarize it in this table. So in full custom design, you have complete design, layout, geometry, orientation, placement of transistor by the designer. It's too time consuming, but yeah, you get a satisfaction while doing that, and that is also something which is really important. However, in semi-custom design, what we do is, some commonly used design, layout, geometry, and placement of transistor in the form of library is utilized as and when required. Also, then in full custom design, you do not need any library. However, in semi-custom design, you have to use a library, and not only one library, multiple libraries. Then development time for design before maturity is more for full custom design. This will become clear when we discuss the next slide. However, development time for design before maturity is less for semi-custom. Since most of these designs are automated, so you can expect that the development time will be lower here, right? Now, full custom design, it has more opportunity for performance improvement, definitely, because you have the freedom to design each and every transistor, to place each and every transistor wherever you want. So in semi-custom design, since it's done in an automated way, you don't have full control over where to place a certain standard set. So that way, it has got less opportunity for performance improvement, and its performance even after the full design time, that is also low as compared to full custom design. Now, full custom design, you do not have like much dependency on the existing technology because you are doing everything on your own, right? However, in semi-custom design, since you are designing all the libraries based on the existing technology, you have to have a very high dependency on the existing technology. And full custom design, since it's requiring more manual labor, and skilled manual labor is much more costly as compared to automated designs or automated softwares or their licenses. So full custom design is high cost, whereas semi-custom design is pretty low cost. Now, let us look at the performance or the circuit performance as a function of the design time for two approaches, which is full custom design and the semi-custom design. So what exactly happens is, as the design time increases, the circuit performance also improves. However, it reaches kind of a saturation after some design time, and that moment, the design time to reach that maturity or the saturation in the circuit performance, that is called the design time till maturity. So that design time till maturity, that is larger for full custom design, and that design time till maturity is smaller for this semi-custom design, because here the tool is giving you all the iterations. Tool is doing all the iterations, so very soon what exactly is the maximum circuit performance that you can obtain. Also, as I discussed in the previous slide itself, that the maximum performance of the semi-custom design has to be lower as compared to the full custom design. So there is a trade-off between design time and the circuit performance, and also the cost. So cost, design time, and your performance. So these three things, you see that there has to be a trade-off. So the question now arises is, if design automation solves all the problems, if it were the best approach for doing digital design and the tool was doing everything for you, why do we even need this course? Or why do we need to study how exactly we design digital circuits? So the answer to this question is, reality is actually too complex, and it's not that easy. Just giving it a HDL and constraint and it does it for you, that's very, I would say, very easy picture. I would say it's not the ultimate reality. So what exactly happens is, the library cells and modules have to be custom designed. Also because, with every passing year, the technology node is changing. The transistors advance every 18 months. So with each new technology, you have to design the library cells and modules again and again. So that is one of the reasons why, the library cells and modules have to be custom designed. More than that, creating accurate black box models, each level of hierarchy takes the lower level of hierarchy as a black box. But creating those black box models, that also requires an in-depth understanding of the internal operations, right? Also, if the design constraints are pretty stringent, and this is the case for most of the modern designs, where we have application specific specifications from the consumer end, and then that makes the designs pretty stringent, and then we have to involve some level of customization. So then your design tools, or I would say those automated tools for semi-custom design, they sometimes do not even give you the correct output, or they are not able to synthesize or design circuits so as to satisfy all the constraints that are given as a design by the consumers. Next is abstraction based design may fail. And why I am saying this, because with transistor scaling and with reduction of that interconnect wire width, what exactly has happened is you are trying to reduce the distance between two wires, as well as you are trying to reduce the width of the wire. So if you're reducing the width, the area of the wire is kind of reduced. So it's increasing its resistivity. First thing, resistance of the interconnects is increasing with technology scaling. And second, since you are reducing the spacing between the two wires, then the capacitive coupling between them is also increasing. So parasitic resistance, that is a resistance of these interconnects should only connect two different modules. But because the resistivity is increasing with technology scaling, now they present themselves as a resistance between two different modules. And also, since there are two different wires, there is also a coupling between the wires, and because of that, they also introduce a parasitic capacitance. So because of these additional problems which are coming, or additional components or parasitics that are coming along with technology scaling, this abstraction-based design may even fail. You may not even be able to satisfy the constraints while designing with your semi-custom tools, as I was also discussing earlier. Also, scaling, as I told already, it exaggerates problem with semi-custom design. So there are two basic things, or there are two main fields where this scaling has an adverse effect. One is clock distribution synchronization, and so clock distribution and clock synchronization, and second is supply voltage distribution. So let us first talk about clock synchronization and clock distribution. So what exactly is a clock? Let us look at that. So to order the sequence of events in any circuit, in any system, basically, we use this clock. So it's nothing but ideally a step function of a voltage. And ideally, it has to reach all the modules at the same time. So clock is kind of, a square wave, a step kind of square wave, which is having a certain frequency. And all the events in your clock, in your circuit, are kind of synchronized with the help at the rising edge or the falling edge of the clock. That we shall discuss while we are discussing about the sequential circuits. But ideally, it's a step function, and it has to reach all the modules at the same time, so as to so that every module is kind of synchronized with something, or every module falls in place. So that is what we need ideally. But what happens is, because of these interconnect parasitics, or the parasitic capacitances which are there in the circuit, what exactly happens is this clock reaches different modules at different instances of time. And when you are working with these sequential circuits, such as registers and something which have to store data, then it may also lead to incorrect sampling. Because, as I told that, these digital circuits, they are sampling some voltage, right? So if the sampling instances are different, maybe, during that time that voltage may have changed. So this may lead to, erroneous kind of, sampling of data in the registers, as we shall see when we'll discuss the modules on sequential circuits. But at the time being, you just understand that, this clock is pretty sensitive, and each of the modules should receive the clock at the same time. And that is being hindered because of these parasitic capacitances, which are introduced because of scaling, as well as because of the components on a chip. The second problem that I discussed was power distribution. So what happens is, all of these modules are connected to same power supply, right? And the current and the voltage that are given by that power supply, it should be stable over time. But what happens is, because the resistance of these wires are kind of increasing, like these interconnect wires, the resistance is increasing, and the inductance, I mean, since they are placed very close to each other, there's also something which is called mutual inductance, which is present there. Because of that, what happens is, even the supply voltage is different for different modules. Why? Because there is some drop between going from one supply, like going from one module to other. The interconnect line has to traverse a certain distance, and within that distance, there would be a certain resistance which would be offered by these interconnects. And because of that, there would be IR drop across that interconnect. And as such, as you go from one module to other, there's a drop in the supply power also, or supply voltage also, that they see. However, we should have uniform supply voltages available at all of the modules. So what people do is they kind of lay these ground and power strips throughout the chip. I mean, it's like you have, so it will become clear as I show you this. So if you say that this is your chip, so then these red lines are kind of your ground strips, and your blue lines are your power strips, or I would say VDD strips. So it is laid like this, or it is kind of like it runs through the entire chip. Why? So that modules placed here, 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 all of those modules can have their individual connection to this VDD line or power line or to the ground. And as such, if they have independent connection to this VDD lines, they don't have to kind of traverse a larger distance in order to have VDD or ground, because only when you have to traverse a larger distance on the interconnect, then these resistances or these parasitic inductances will come into picture and kind of reduce your supply voltage as compared to what you have exactly given to the supply. Now with this understanding and this motivation of why we need to do this course and why we need to understand how exactly we have to make these digital systems, let us move to the recent developments that have taken place in the world. So the first development is in the development of this IoT. So we are living in an era of Internet of Things. So all these devices, smart devices, form a part of this IoT. They are interconnected and also connected to the internet in some form. So what forms the part of this IoT? Modern healthcare systems, which kind of store data on the clouds. Modern appliances, which also store data in the form of clouds. Your smart devices, smart watches, wireless IoT nodes, everything, they are now interconnected, and they are connected via the internet as well. So we are living in a hugely interconnected world. And this IoT has led to something which is called as data explosion or big data. So these devices, they communicate amongst each other and also with the cloud, right? And because of that, there's a huge amount of data, like data transmission. So in the present world, in 2020, around 44 zettabytes of data was being transmitted every second. So what exactly is 44 zettabytes? So 44 zettabytes is 44 trillion GB data per second. You can understand the amount of data that we are handling right now. And also the amount of revenue that it has generated is $7.1 trillion, which is like 1,000 times more as compared to the GDP of India. So IoT is the new normal, I would say. And because of this data explosion, it has also opened a new field which is known as big data. So the data from these sources, as well as from these social media and everywhere, is kind of being sent asynchronously. Why asynchronously? Because it is not synced with any clock. Here, the data is coming as and when required, and it's not synchronized with clock. However, this data, huge amount of data, which is now being transmitted, has to be stored somewhere for processing, right? So what are the major sources of this big data? So it's coming from healthcare sector, from travel sector, from education sector, telecom sector, e-commerce sector, media and entertainment, retail, finance. So these are some of the entities, or I would say some of the sectors generating huge amount of data. Now these huge amount of data needs to be stored somewhere. It needs to be processed. And so nowadays you have a large amount of cloud servers, or you have a large number of, you must be hearing about these data centers and all. So they are there just to process these data and store these data. And also another big development in the recent past is artificial intelligence. So we are right now going through an artificial intelligence evolution as well. Every industry wants intelligence. It has got AI has got multiple applications, and these applications have been rising rapidly, right? So from 2013 to 14 to 15, you see a rapid increase in the amount of artificial intelligence that was being used in your industries. Also, they have also become part of our everyday lives. I mean, all of you must have used OK Google, Alexa, Siri. I mean, the rich ones would have used Siri, but Alexa, OK Google and all, I mean, almost everyone would have used it. And you use it on a daily basis. Even your Snapchat camera filters and all, you also use AI. So it has also become a new normal, I would say. However, all these applications, they have led to a shift. Like I would say that there has been a shift in applications. So earlier, the processors used to be like, they used to do something which was in the compute-centric paradigm. So what exactly is compute-centric paradigm? So computing or processing was the main kind of focus of this compute-centric paradigm. So what was it? So we had to solve some differential equations or something. So there the bottleneck used to be the interaction between CPU and memory. I mean, as I'll tell you later also, these systems are kind of von Neumann, the modern CPUs, they follow a von Neumann architecture where CPU, that is a processing unit, or I would say where the ALU and the memory, they are two different blocks. So whenever you have to process anything, you have to, like, you know, send data frequently between CPU and memory. I mean, the logic processing unit and the memory and the memory. And that is heavily energy intensive, as well as that also adds to the latency. So because of that, you know, your system's so pretty slow, or the clock frequency has saturated over the years. I mean, 10 years back when I was purchasing my laptop as a bachelor student, then the clock frequency was 3.1 gigahertz. Now, when I was purchasing my laptop as a faculty, the clock frequency is still 4.1 gigahertz. So, you know, by this end of 10, like within this 10 years, the clock frequency got only increased by 1 gigahertz. However, if I look at my mobile phone memory, so when I was buying my first mobile in my bachelor's, the memory used to be 2 GB or something. And nowadays, you won't find phones with 2 GB. At the least memory that you'll get is 64 GB. And that is also expandable to 256 GB. So you can understand that there has been a huge, I would say, order of magnitude change in the memory, order of magnitude increase in the memory. But if you look at the processor speed, it has remained all the more same. That is because of this bottleneck, which is also called the memory wall. That is, you know, every time you have to access any data, it leads from a memory, it leads to a large amount of energy, as well as it adds to the latency. But from that, now what we have shifted to is a data-centric paradigm. We have a huge amount of data, we have to store them, and then we have to analyze them as well, right? So nowadays you will see that, you know, there are a lot of new paradigms coming up, like data analysis. This has become the new, I would say, earlier people used to go for MBA in finance and all, but now people are choosing this data analysis jobs, right? So this has become the new focus of, you know, even the jobs and all. And here, what limits it is the bottleneck is storage and I/O. So you have to store this data somewhere for, you know, searching and mining this, right? So this is how, you know, there has been a paradigm shift in the application. Also here, if you notice carefully, I referred to this as memory, and here I referred it as storage. So what exactly is the difference between memory and storage, or are they the same entity? So what happens is, memory is something which is pretty fast, and it's located close to the CPU, while storage is something, so another property of memory. So since it's very fast, it's located close to the CPU. Also, the capacity is low. For instance, your cache or your DRAM or main memory. So your cache and DRAM, they are very small in size, right? Your cache is hardly a few KBs. Or nowadays people have, like, nowadays laptops come with some MB of flash of cache memory. That's very fast, but you know, they're like I would say they're very costly, and at the same time, their capacity is memory capacity, or I would say storage capacity is kind of limited. What I call as storage is your hard drives, which could, you know, analyze or which could store these petabytes of data. Your hard drives, your SSDs. So they are huge in size, right? There is some terabytes, so you can actually store a large amount of data, or your magnetic disks. They are kind of storage class of memory. So memory and storage are not same quantities, they are different. Main differences: memory is ultra fast, capacity is low. Storage is slower, but storage capacity, like the capacity to hold data, is huge. So that is the main difference between the two. So now let us look at some of the advanced computing engines. So the first advanced processing engine that you must be aware about is a GPU, or a graphics processing unit, right? So whether it is a CPU or a GPU, the inherent architecture is still von Neumann architecture. That is, memory and processor are two separate blocks. And the moment you have to process anything, you have to, you know, fetch memory, fetch the data from memory. And this data transfer from memory to the processor is kind of, you know, it's not only, I would say, energy intensive, energy hungry, but it's also, I would say, it also adds to a delay. So this chip over here shows NVIDIA Turing, which is the most advanced kind of GPU from NVIDIA. It, you know, this simply brags its capabilities. So it can perform 8.1 tera, that is 8.1 into 10 power 12 max. Max is nothing but multiply, accumulate, operation. So multiply is simply multiplication and accumulate is addition. So it simply performs 8.1 tera, that is 8.1 into 10 power 12, multiply and accumulate operations per second while consuming 36 watts of power. Now, if you look at your mobile phone, the battery is like 5 volts and the maximum amount of current that you can extract from it is close to 1.2 amps. So the maximum amount of power that it can drive, or the maximum amount of power that it can give you, is well less than 36 watts. Now, since it is pretty less than 36 watts, you cannot actually install this NVIDIA Turing GPU in your mobile phone and perform some applications. However, if you notice carefully, these AI applications, they require a GPU to run, right? You have to train your models, your AI models on GPU for several days, and then only your AI models give you perfect classification answers or whatever you are using it for. So you have to have some way to enable these advanced processing engines in your mobile devices, and that is the way going forward. So what exactly happened was, Google tried to reduce the distance between this memory and processor. So it came up with this chip which is known as TPU. So TPU shows you 92 into 10 power 12 multiply accumulate operation per second while consuming 40 watts. So although the number of operations that it could perform improved significantly, but the power was nearly the same, right? Even 40 watts cannot be delivered by your mobile battery. So what kind of architecture did it use to improve this performance? It kind of brought the processing unit, which is ALU, and cache very close. I mean, this DRAM is close to ALU, and this gray thing over here, this is the cache memory. So it increased the amount of cache memory in the system, and it made this ALU as close to this as possible, so that the data transfer is as smaller as possible. So the data bus distance is very small. That is what it did. But even after all these things, we cannot reach an energy efficiency which is of the level of human brain. So human brain is kind of considered as the most efficient engine that we can make. And in the human brain, what happens is that your memory and processor are not two separate blocks. It's not a von Neumann architecture. It's a non-von Neumann architecture where memory and processing is happening at the same time at the same place. For instance, while you are listening to this lecture, some amount of it is being stored in your memory. I mean, you are also able to store some amount of this data, and at the same time, while listening itself, you are able to process it. So memory and processing both are happening at the same place at the same time. Also, in your brain, the basic constituent, or I would say the basic processing element, is nothing but a neuron, and there are like 100 billion neurons there. And each of these neurons are connected to 100 to 1000 neighboring neurons with the help of these synapses. So these synapses are something which just control the connectivity between the neurons. So there are like 100 trillion synapses occupying only 2 liters of space in your human brain. Just understand how complex or how dense your brain is. However, this neuron, if you compare neurons with transistors, I would say in 2 liters of space, you can accommodate more number of transistors as compared to the neurons. So neuron size is kind of larger as compared to transistors. So that way, in terms of area, we have already beaten human brain. But in terms of energy efficiency, no. Why so? Because it consumes only 20 watts of power. That is a power equivalent to one of the LEDs that you light up in your home in order to do a day's of work. So that is so great thing about it. Only 20 watts of power. Also, you are able to process everything real time. Now, why I want to bring this point is, because in modern systems, in modern computing systems, or in modern wires and all, electricity is conducted with the help of electrons, and we know that electrons, their speed is pretty fast. However, in your brain, how exactly these informations are propagated is in the form of ion conduction. I mean, in your brain, it's basically those. It flows with the help of a diffusion process. Your calcium ions are basically responsible for transmission of information between 2 neurons. So what happens is basically the calcium concentration is increased in the medium between the 2 neurons, and as such it diffuses into the neuron, and that is how basically this information is transferred in a human brain. So even with ionic conduction mechanism, we are able to process everything real time. What this means is you do not need to go for ultra high frequency of operation. You can work even with some megahertz of frequency of operation. So there is a new paradigm which is opening up, which is also known as neuromorphic computing. What it simply says is it's inspired from the brain. So in neuromorphic computing, we take inspiration from some of the principles of the human brain, and then we make some VLSI circuits in order to mimic those operations. And that way it becomes much energy efficient as compared to your pure digital systems. However, it may be noted that even these neuromorphic systems can be digital. So now, how can we make these biological plausible systems? So if you look at these functions of the neurons, what exactly happens in any of these neural networks, or I would say what exactly happens there is these inputs to the neurons are kind of weighted by the synaptic weights. I mean, the inputs are kind of multiplied by these synaptic weights before being transferred to the other layer of neuron. And the basic operation that is happening at the neuron is a vector by matrix multiplication. So whatever inputs are coming from the sensory nodes, such as your retina, that is kind of being weighted, or that is kind of being multiplied by the synaptic weights which are present in your, I would say, brain. So these synapses carry some weight, and this input information from the retina is kind of multiplied by that. And in the ganglion cells, which are basically your neurons in the brain, what happens is vector by matrix multiplication is performed. That is, you add the product of the input information with this synaptic weights, and that is kind of the input of this neuron. So you first perform this vector by matrix multiplication, and before sending it to the next layer of neurons, they just perform some I would say filtering operation, or I would say they apply some kind of function, nonlinear activation function on this information, on this vector by matrix multiplication. So how can we realize this kind of a function on a hardware? So if we have a crossbar circuit like this, so what exactly we have here is, so between each of these rows and columns, we have one adjustable conductance. So this conductance value can be changed. Now, if we encode our inputs in the form of these voltages of each row, and if we encode our weights in the form of these adjustable conductance. So in your neural networks, as you may know, that you have to change the weights in order to increase the functionality. So if you encode these conductances in the form of weights, then what happens is this current flowing through this node is simply V in 1 times G11, right? So it's V times G. So Ohm's law kind of takes care of your multiplication, V times G. So input is V, weight is G. So V times G is simply performed by Ohm's law. Now this is V in 1 times G11. Now the current flowing through this is V in 2 times G12, and the Kirchhoff's law will kind of add these two currents. So all of these currents would be added up. So accumulation operation is kind of performed by Kirchhoff's law, and multiplication is kind of performed by Ohm's law. So at the end of this column, the current that is flowing through it kind of represents your vector by matrix multiplication, which is the basic operation that happens in any neural network. So if we have this kind of crossbar circuit, then we can realize this vector by matrix multiplication. However, this idea is not new. It was present in 1980. Carver Mead at Caltech, Professor Carver Mead at Caltech, he was kind of developing these neuromorphic systems. Here, one more important thing to note is that it's a non-von Neumann architecture. You are storing the weights here, right? So you are storing the weights here, and you are performing the product also here. So it's like your processing and your memory both are in situ, or I would say at the same place. So it's a non-von Neumann architecture. Also, the reason why these circuits could not become popular until recently was that there was no such efficient adjustable conductances or adjustable cross-point devices like this, which would store the data, as well as where you can change the data just by applying electrical pulses. What happened recently? So in 2008, my postdoc supervisor, Professor Dima Strukov, or Dmitry Strukov at University of California, Santa Barbara, found this missing memristor. And those memristors could be used as these adjustable cross-point devices. Now, what exactly is memristor? So memristor is the fourth fundamental element. Just like you have resistance, capacitance, inductance, there is something which is called memristor. And this was kind of the missing link between your magnetic flux and voltage. So there was nothing which would relate these two quantities, and that is why people came up with this memristor. Now let us look into the future. I mean, I told that I would also let you know what exactly is the future. So a peek into the future, we'll have a lot of neuromorphic ICs. Some of them are already developed. So we'll have some amount of CMOS neuromorphic processors. Like we already have Intel Loihi, which is the best to accelerate spiking neural networks. Recently, IMEC, along with Global Foundries, also came up with its 22 FDX based neural network accelerator. So this uses SRAM as memory, and it performs in-memory computing using SRAMs. So SRAM is something that we will be covering in this course. And these SRAMs are kind of, simply replacing these adjustable conductances in this case. Now, the second is hybrid CMOS non-volatile memory-based accelerators. So non-volatile memories are kind of emerging memories, which can also be used as, those adjustable conductances. So one of them was this RAM-based accelerator. So when I talk about this hybrid CMOS NVM, what I mean is the back end of line, or I would say, you have some transistors as well as some memory. So that is why it's called hybrid CMOS NVM based accelerator. So those transistors are silicon based. They are CMOS based, complementary MOS based. I'll let you know what exactly is complementary MOS when I discuss about inverters. But you just understand for the time being that they use silicon transistors as well as some non-volatile memories. And then this is something which I worked on during my postdoc. So this was one. Then you also have a inference accelerator chip from U Michigan, which uses RRAMs also. Then the first kind of hybrid chip was it was formulated by IBM, and it was called TrueNOT. So these use phase change memory devices along with CMOS. And recently HP also came up with its own dot product engine, or that vector matrix multiplication thing is also called dot product. So HP came up with this dot product engine where these three are kind of their 1T1R or RM crossbars, and this is CMOS circuitry. There are comparators, ADCs, and all those things. So we can also have emerging or exotic device-based computing primitives such as carbon nanotube and non-volatile memory-based computing primitives. So Stanford's hyperdimensional computing chip. So what exactly is hyperdimensional computing? So in your brain, what happens is our brain doesn't compute in the form of Boolean variables. I mean, information is not represented by a single Boolean variable. What happens is each information is kind of encoded in a hyperdimension. By hyperdimension, I mean it is encoded in a bit of streams, and that stream length can be as large as 10,000 streams. I would 10,000 bits. So each of the information bits in our brain is mapped onto those 10,000 bits. And then what happens exactly? What is the advantage of that? While processing, even if some bits are corrupted in that encoded version, the overall function doesn't I would say suffer much. So that is why your brain is able to do things in such an error resilient way, because information is encoded not in the form of single Boolean variables, but it is encoded in the form of hyperdimensional bit streams. And here in this chip, what they did was, at the back end of line, they kind of integrated, they made carbon nanotube based gates, and on top of that, they used adjustable conductances in the form of RM. So they kind of fabricated them one on top of each other, or they realized it in different layers, I would say. So bottommost layer, it's kind of performing logic gates. The layer which is at just the top of it, it's performing some memory as well as processing operation. So these are some neuromorphic chips which I would say that you may encounter much going 5 years down the line. Now, apart from this, another field which is developing recently is called quantum computing. So you must be listening about the news coming from Google, Microsoft, IBM. So there has been a rat race for making a good quantum computer between these three giants, and they're kind of investing hugely on this. So what exactly is quantum computing? So unlike digital computing, where you work with the logic bits, which are 0 or 1, here you work with quantum bits or qubits. So what is so special about qubits? So unlike digital bits, they follow a principle of superposition. What exactly is the superposition? So this superposition means that they can remain in two states at the same time. I mean, this may sound perplexing, but it will become clear how exactly one thing can remain in two states at the same time. So in digital logic, bits are either 0 or 1 at one time. However, if you represent 0 by heads portion of a coin and 1 by tails portion of a coin, and if you spin that coin, so calling heads or tails in a spinning coin is same as having a qubit. Now these qubits, since they are traversing different configuration while spinning, so they kind of perform several calculations at once because of this superposition thing, and they are best suited to solving optimization problems. Optimization problems, there are some problems like traveling salesman problem, max cut problem. I don't know if you have learned about that, but they require optimization. So let's say I have warehouses at several places in the country, and I have to deliver some product to some places. So how basically I'll optimize my path so as to traverse the least amount of distance between warehouse and those consumers. So that is some kind of optimization problem. However, these quantum computing primitives, they don't work well with classical algorithms like simulated annealing. I won't get into details, but you should know that these quantum computers, they require development of dedicated quantum algorithms. The algorithms with which the classical computers work, they won't work efficiently with these quantum computers. Also, there is something which is called quantum entanglement, which allows two different qubits to link together and perform even complex functions. And the number of functions that can be performed kind of increases exponentially, or I would say even super exponentially. However, the problems with these kind of systems is that these qubits are stable at ultra low temperatures, some millikelvin temperatures. So it requires a huge amount of power to cool these chips or cool these systems to this some millikelvin kind of temperatures. So that kind of I would say inhibits or limits its energy efficiency.